Okay, so this lecture we'll talk about the underlying process to how things get to the screen. Um, so in other words, the rendering pipeline that the game engine uses under that, and engines in general. There are, of course, specifics that differentiate each engine, but we're going to talk fairly broadly. So to start with, this is a close-up rendering of an LCD screen, right? And so each individual pixel is made up of three colors. We get a red, a green, and a blue. And depending on the amount of light of each of these, you see a different color. So if you were to walk away from this image far enough away that it started to blend together, you would actually see a white or gray image from this. And the reason for that is because your eye tends to blend these colors together, and there's a lot of sort of interesting and complicated things that your eye is doing with the light that it perceives, especially at a resolution below what your eye is able to process, right? Um, but the usefulness that we can derive here then is that the pixels on the screen blend together and make an image by simply combining different values of red, green, and blue. And so our job in the rendering is to decide how much red, how much green, and how much blue to provide at every single pixel on the screen at any moment in order to convince us that we're seeing a fully rendered 3D world, right? Um, so at the lowest level of handling this, then, what we have is what's known as a frame buffer. And the frame buffer, you can think of either maybe as three sheets of data or an array of 3-byte data items, or even 4-byte data items, really an integer. Either way you think about it, what happens is we look at each of the bytes, and each of the bytes at each position in the frame buffer corresponds to a pixel on the screen. And so if you are rendering at 1920 by 1080, which is kind of the standard high-def resolution currently, then you have 1920 by 1080 values in your frame buffer. But you have one byte value for each of red, green, and blue. At least currently, and of course this is changing a little bit in terms, but we'll just worry about single bytes going from 0 to 255. So a single 8-bit value can represent, we go from 0 to 255, and 255 is maximum intensity, and 0 is minimum intensity. Okay? So we get three values, and we say if we've got, say, 255, 255, 255, then what we're really dealing with is a white value in that case, right? And if we have 0, 0, 0, then we're getting a black value, or no intensity coming through. And so we really get what is known as the black value of the monitor, which is usually an active response and something more like a dark gray. But in any case, it's usually looks black, right? And so right now, even as you're looking at this video, probably the edges of the screen look black, and the main part of the screen looks white in the background. And those are because we are turning off some of the pixels and turning on some of the others in the frame buffer by setting those values. And so this all kind of happens in the background. So we really set the frame buffer, and then there's a process which just feeds this information to the screen, the monitor itself, in order to do the rendering. And I'm actually showing a CRT raster, but what really, these days there are very few CRT screens, but the process is essentially very similar in terms of how the communication happens to talk to the monitor and send the data over. Once we've written the data into the frame buffer, it will show up on the screen. So our job then really isn't necessarily to write directly to the screen. We write directly to the frame buffer and then assume that that's getting to the screen. Okay, so now that we have the data in the frame buffer, we need to understand to some extent how that data gets onto the screen because there's some important details that occur when that happens. So what we're showing here is the scanline conversion of the frame buffer to the screen. And what's happening is that we move along these horizontal lines and we read the values out of the frame buffer and represent those as intensities into the screen. So what's happening is there's a device that's moving through and actually changing the intensity value on your screen based on the value in the frame buffer. So if you have a 0 there, it's going to change the intensity to 0, If you have a 255, it's going to change the intensity to full, whether it's red, green, or blue. And of course, as we know, if you move far enough away, you see sort of the grayish color that's represented by the combo of those three colors together. Or you really don't see them as individual red, green, blue unless you get very, very close to the screen. So, and in the CRT displays, this was literally a laser gun kind of thing that would shoot photons at the screen and light up the medium. But in both cases, what's happening is that the pixel, the liquid crystal, the phosphor, are being illuminated temporarily, but quickly enough that they stay active, and your eye processes a solid color that doesn't flicker, unless you're very sensitive to it, and then maybe you'll actually see the color or the flickering, and so that's related to the refresh rate that you hear in your monitor. So as we move through this line, we see that we go left to right from the top left of the screen over to the right hand side. We read all of the pixels, and so you can imagine that what we're seeing here is all full intensity, so white pixels are being rendered, and we move through the scan lines and we're refreshing at a white pixel. And then when we get to this line here, we see a black pixel in the center, and we move on and we render more white pixels. And then we get it on, we see a black pixel here, a white pixel, black pixel, and then more white pixels, and so on. And so what happens is that your eye then sees the letter A on the screen, and in fact it sees it at a much higher resolution than what you're seeing here, right? This would be a very low resolution render. It's also seeing it refreshed at, say, 60 hertz or 70 hertz, whatever your monitor is, where it draws this whole line, it does this whole scan line every single time, right? And so there are two synchronization events that happen. One is that as we're moving from this position over here, the right position back to the left, so this dotted line that moves, it's called an H-sync, where we move across our scan line and then back to the beginning of the new line. And we don't necessarily pay attention to the H-sync. I believe internally that's used to let the communication between the monitor and the video card know that it's on to the next scan line and needs to start sending new data. But the other important one is what's known as a V-sync. And the V-sync is when we move from the lower right down here back to the upper left. And the V-sync is an opportunity for us to change the frame buffer without necessarily changing it in between. And we'll see why that can be a problem later. So that's one of the important pieces that comes in, as it's a small amount of time, so it's a very small window. It's 1/60th of a second or 1/70th of a second, depending on the refresh rate of your monitor. But as we've already seen, in many cases, our frame rate, our FPS, is probably much higher than that. And so just being able to change the frame buffer, assuming that we already have one in place, it becomes a very easy process for the computer to do very quickly. And so that's essentially the scanline conversion, and that's how we actually get the image to the screen. It's surprising to think about how much activity is happening, and yet what you see on the screen is a solid image, right? But of course, as you can imagine, by changing the frame buffer underneath and changing it very carefully, you actually get animation, and very smooth looking animation, in the same way that you see a very solid image. So let's take a brief aside and talk about hexadecimal values, at least to the extent that we need to talk about color. So hexadecimal values are a convenient way of representing what we get out of 4 bits, right? So if you remember, or if you've heard, or if you didn't know, a byte is 8 bits of data. So a 0, 1 is a single bit, and we have 8 bits that all can be turned on and off. And by looking at the number of possible combinations of on and off of 4 bits, we get 16 values. It's 2 to the 4th. And that's the number of combinations, and it's important only that you know that it's 2 to the 4th, so that it's 16 values. The way we represent that is by giving the standard decimal of 0 to 9, which gives us 10 of the values, and then we use A through F to represent the other 6. So this is the full reference of 16 values, and you can convince yourself by counting through that you get the full 16, right? So 0, of course, counts as a value in its own. And then also we get A represents 10, B represents 11, C is 12, and so on down the line here. So this value, this 10 in hexadecimal, is actually the value 16, right? Now it's important to remember that there are 16 possible values, but with 0 is one of them, then 15 is kind of the maximum we represent. Now, because we have a full byte and we have two half bytes or 2 4-bit values, we actually use two hexadecimal values to represent that. So one hexadecimal value represents 4 bits for 16, 0 to 15, and two hexadecimal values then represents 16 times 16, which is 256 different possible values. So with all of the combinations of 8 bits or two hexadecimal values, we can represent any number from 0 to 255. And so as we've already heard me saying, 1 byte in our frame buffer counts for a single intensity for our, say, red channel or blue channel or green channel for a given pixel. And so what you'll see then is a pair of 3 values, or a vector of 3 values, often represented as hexadecimal for the convenience of representing them, that represent the full set of 17 million colors that we can manage in a full RGB suite. Right. So 17 million is the 256 times 256 times 256 possible values. Now it turns out that your eye can detect quite a few more, and there's some variation in terms of the actual intensity. So if you imagine the sun versus, say, a dark night, there's actually quite a bit of intensity difference rather than just simply 0 to 255. So we'll talk about that more, but what you can think of this is in terms of the 0 value versus the 255 value is simply the minimum intensity that the monitor will show, and sometimes that can be an active black value, as we might see on the side here, or 255 would be the maximum intensity your monitor is able to show. And that intensity is generally within some range that is comfortable for you to view, hopefully if you set your monitor correctly and you don't have eye strain. But of course, that is not the full intensity that your eye can see, and so we'll address that later. So, so how do we get images to the frame buffer? So the simplest way is if we imagine that we have a scene rendered into the frame buffer right now, and we won't worry about how we got that scene into the frame buffer. We'll just worry about that it's there, right? And we know that we want to draw this character down here at this position in the world. So what we'll do is we will, one, capture the rectangle behind which the character is going to live. So we assume maybe that the character's full sprite size is the same size as this rectangle. Some of those pixels might be marked as transparent in the sprite that we're dealing with this character. We can worry about that in a minute. But what we do is we capture the background. We store the current state in the frame buffer. We actually read the values off of that, save it off into memory somewhere. We can write our character in there, and then what that lets us do is now we know that this was the area that the character was in. So the process is kind of a similar version to our scanline rendering, and what we do is we walk across our sprite and we read each individual pixel on that sprite. And if we've got a careful encoding, we might say that either we allow for an alpha value, which is a 4th value that represents how transparent that pixel is, or we simply say, and in the older days we might have done this with only 3 with only 3 color values. We'd specify something like a pink or a weird green or some light blue or something as our transparent color, something that we wouldn't probably use ordinarily, and pick that one color out of all the colors that we could possibly represent, and that one represents our transparent pixel. And so if we see that color, we simply don't draw, right? We leave the background as is, but every other color, as we see it in the sprite, as we're walking through our little image, then we render that pixel onto the background, into the frame buffer. We copy it from our sprite into that position in the frame buffer. And then we move down to the next line and so on. So we'd actually do a scanline conversion of the sprite into the larger frame buffer. But we would also save the background because then we can write back over top of our sprite and erase our character. So this process is known as blitting. I don't remember the term. It actually became so common that it became a sort of a native function that you could do, that you could specify a sprite and a region within another area, and it would essentially just do the memory copy for you. And so that terminology continues to exist. We don't use it as often anymore because we don't really need to worry about doing this level of sprite control, and often we're rendering the full frame. But before computers were fast enough to very easily render the full frame, doing this kind of careful update of rectangles within the screen, only updating as necessary, was the way to make it fast enough. Now the one trick that we did run into, and that was solved by the same guys who actually wrote Doom, is actually solved in two ways. One, it was solved for Mario on the Nintendo, but they had specialized hardware that took care of it. And then the Doom guys took care of it for a game called Commander Keen. And that is that they, in order to scroll, you really do actually need to change the entire image, right? So if we want to move all of this image left, say, a few pixels, then in order to do that, we really have to modify the entire image. And so what the Doom guys did for Commander Keen was figure out a trick where they could essentially copy the frame buffer back into itself very quickly, rather than having to do a complete, a complete copy of all the pixels involved. Even though it's only like 320 by 250, that was enough, and computers were slow enough back then that would have caused the game to run very slowly and not run at, say, 30 frames per second. And so by doing that, they could move the screen over to the left, and then all they needed to do was draw a series of sprites, and usually that's why the background is even described as a series of sprites. They could just do small rectangles to render in the background and draw those in. And so they would fill in just the small version of the right, and then you could have the full screen move. But of course, before that, everyone was doing just splitting, and you'd see a full screen of graphics. And probably if you hit the edge, it would freeze frame, clear the screen, and then show you a new background view entirely, because that was the way things were done. So games like King's Quest did that, or Lode Runner was a single screen game. Pac-Man, of course, was a single screen game. So side-scrolling was a pretty interesting invention, especially for the PC, to make it possible to do the same things that you were getting with specialized hardware that Nintendo was pulling off. Okay, so coming back to our VSync issue then, if you're not paying attention to when you start writing into the frame buffer, then you can get what's known as screen tearing. And so in the Blit world, that looks something like this. Now we still see that occasionally in current games because it can happen in the same kind of way. So if we imagine that we are currently drawing the screen, we're doing our rasterization. Of course, this is a very high-res screen, so I'm not going to try to draw all of those scan lines with my mouse here. But as we're moving through, scanning, moving left and right, rendering pixels out of the frame buffer, right here, we actually start writing into the frame buffer again, right? So the monitor is currently rendering this line, and we also happen to be rendering into our frame buffer. We're actually doing the Blit operation. And so we've started copying the data up here, but then we're pretty fast on our computer, and so we started copying the data up here, but we made it here before the H-sync finished, before it moved from here back to here. And so by the time it gets down here, it's now reading our updated frame buffer values, right? And so this is problematic because now we're rendering only half of this guy. It only happens for one frame. In the next frame, he will be entirely there. But it's enough that the pixels change and the continuity, this sort of solid level of continuity, skips. And our eyes will notice it, our players will notice it, especially the very astute players and the ones that like to complain. And so the way we resolve that is that we actually read the VSync signal, right? And so in the Blit days, we would read the VSync symbol and that, or signal, and that would be the time that we might do the the Blit operations, right? So we maybe render our dirty rectangles and then render out those specific areas of the image that we needed to change while that VSync is happening. So we'd wait until we see that it hit down here, and then we'd say, okay, during that time, real quick, write everything, because we know that it's not doing any rendering of the screen at this moment. It's that 1/60th of a second that it has to move from down here to up here before it can start drawing the full screen again. It's actually even shorter than 1/60th of a second. 1/60th is the full time it takes to render all of that and then get back at the top. So anyway, so given that short time, you render real quickly in there. The other approach that's taken is what's known as double buffering, and that is that you actually write to a second copy of the frame buffer. So while you're currently rendering the screen, there's a single frame buffer that the video card is reading from, but then there's a second frame buffer that you're writing to, that you're using as your source for kind of your scratch pad, right? So while you're trying to build up the scene, the next frame of the game, and again, we're doing 30 frames per second, so the next frame is a very short time away. But we have a few moments to build that up, We build up those changes, and then during this process, we copy that buffer over. Now this is doing a full screen copy, and so this requires more modern hardware where we can afford to do the full screen copy, or we'd have to do a lower resolution or something. One thing that to note then is that it does tie your rendering rate and sometimes your full update rate to your monitor. And so there are some games where it's important to have, or some game engines that exist where it's important to have update rates that are faster than 60 hertz because you need that precision on your input and you need that precision on your update. And so by tying ourselves to the monitor, then we might actually freeze our entire update loop while we wait for that monitor refresh to happen so that we can do our frame buffer copy. So that's one of the reasons that we might do it. It might pay the cost of both doubling the memory and having to do a full screen copy every time. So I mentioned a couple times that it was the Doom guys, John Carmack, and to a lesser degree Michael Abrash, or Abrash. I'm not sure how to pronounce his name correctly. So Michael Abrash joined the team with Quake, but he was somebody that John Carmack was actually reading and learning optimization tricks from while he was working on some of these other projects like the Doom game and I think Commander Keen as well. What's kind of funny about that is that this whole process of rasterization and the issues that come there has actually come back again in the form of VR. So in VR, we're trying to render two screens directly in front of your face and on your eyes inside a headset. And these are two small LCD screens that render at something like 1280 by 720 or even 1920 by 1080. But they're still doing that full scanline process. And so it turns out that if you move your head while the scanning is happening, you get not just screen tearing, but you actually get the lines moving where you're seeing a different view a few lines down than the one above you. And so what happens is you get some, like straight lines actually end up looking something like this, where you'd expect a straight line to look like this, but it ends up skewing because of the fact that you're rotating your head as you go. But it's kind of interesting to see what happens. And you can actually see the full effect, which can be very jarring if you were, in a VR world and actually had this level of screen shearing happen because you're turning your head while rendering. So anyway, it's kind of an interesting point to note that although this whole scanline conversion and blit thing is very old and from the early days of graphics, it still comes back to haunt us, and so it's important to remember that it's good to understand what the underlying technology is doing. As sort of another way of talking about building up our frame buffer, I want to talk about a technique called the painter's algorithm. So this idea comes in again with really 2D rendering, but it still happens with 3D rendering in some ways as well. And that's the idea that in order to render multiple levels of things, so like what we see here is kind of a deep background, a far view of this mountainous view, right? And then we kind of see a mid-range view of the terrain that leads up to the mountain. And then we see trees in the foreground, right, or the relative foreground. And we might even have our character in front of the trees as well, so we might actually have our character moving in the side scroller over here. And so the reason for this is that we will probably, in this case, need to render the full screen every time. But it allows us to avoid the problem of figuring out which things come first, or making sure that things in the background don't overwrite things in the foreground. And so we actually start to define very specific layers. So we come up with, say that I'm going to actually create multiple channels and have, say, a background channel, a midground, and a foreground. But this notion lets us deal with both the fact that we don't want to erase things, right? So if we were to render the mountain on top of the trees, we'd actually end up erasing the trees here, and it would look entirely incorrect. So this makes it very easy for us to do, to kind of keep control of what we're rendering. And although we are sort of rendering this piece of the mountain, and then we're overriding that piece with the terrain, and then we're overriding parts of the terrain with the trees, we can kind of afford that, especially in the more modern period of time, in order not to have to be any more clever about figuring out what regions we don't want to erase. So this is a little bit different than the dirty rectangles, right? This is kind of the the alternate approach to that, but does require that we set things up in layers. One of the things that falls out of that, however, is the ability to do the parallax effect. And so this is kind of a pseudo 3D effect where what we do is we render the far background, so assuming we're moving from, say, left to right in this case, we render the far background as moving somewhat slower, like scrolling somewhat slower to the left as we move than the midground, and then that's moving somewhat slower than the foreground, right? So these buildings in the foreground are moving to the left very quickly. The buildings in the midground are moving to the left somewhat slower, and the buildings in the back are moving fairly slowly entirely. And you might even have a far background where you have a moon that doesn't move at all, right? Because relatively speaking, we never see the moon actually move, right? And so this is a 3D effect because if you say, imagine yourself driving along the freeway next to a mountain, and since I'm in New Mexico, I'm going to use a reference to the Sandias, which, if I'm driving north on I-25, are the mountain off to my right, I believe, or my left, unless I'm mistaken that. And when I see those, I see them, I can pick a point in my window, and that point will kind of stay with me for quite a while, right? And even though the mountain looks tiny, it appears to move fairly slowly relative to where I'm sitting, right? And the reason for that is that the mountain is probably, 10 to 20 miles long, right? And so it actually takes me the same 10 to 20 miles to travel past the mountain as it would if I were traveling up close to it, right? So if I were traveling at the base of the mountain, I would have to travel 10 to 20 miles to get from the sort of southernmost end of the mountain to the northernmost end of the mountain. So even though I'm far away, I'm maybe 10 miles away or 20 miles away driving on the freeway that's far away from the mountain, and the mountain looks very small. It fits inside my window now. But I still have to travel 10 miles for it to go. And so what happens is it's really a factor of the fact that the mountain is sort of scaling, and it's this a shrinking effect that happens, the horizon effect, where things that are far away look smaller than they actually are to our eyes because of the way the light comes in and all these kind of factors. But the physical reality remains the same. The fact that the mountain is 20 miles long and it takes 20 miles to traverse it, its distance, still remains the same. And so the effect that happens is that it appears the mountain moves slower to make up for that. It's almost like relativity, but not really. Time is not dilating, space is not actually dilating either. It's simply our perception of things that's dilating. But we can take advantage of that same effect by making a small mountain in our background and having it simply move very slowly. Whereas foreground things like small trees or whatever, which we're driving by on the road, or small bushes, those are moving very quickly. Okay, so let's go from one illusion to another. So I take a lot of this from this website here, and again there will be a link available for that, so you can go and look in more detail at this. This comes back to why we tend to see motion and where that kind of breaks down. So I see this ball moving at the bottom. I believe this ball is moving at 24 hertz, and then the top ball will start moving here in a second. Oh no, yeah, it is. Okay. So the bottom ball, so both balls are moving at the same physical rate. The bottom ball is moving at 24 hertz, and the top ball is moving at 60 hertz, or 60 frames per second. And so we see that moving smoother because we're seeing more frames, right? And so we're seeing smaller jump. We're seeing smaller teleports between these two. Down here we're seeing larger teleports. And of course it probably looked a little funky even when you saw the 24 frames by itself, but it's certainly a difference in smoothness between the two, right? So your eye is able to see a difference up to 60 frames per second. Once you go beyond 60 frames per second, it becomes difficult for your eye to tell a difference. Now you might also ask, what's the sort of lowest end of where you can see something, and it's around 8 hertz. So if you see images updating at about 8 times per second, that's about the minimum at which your eye will suggest that you're seeing motion, as opposed to just a few still frames or even just juddered images that are flickering and making your eye hurt. Right? And so as long as we're moving fast enough, we can convince our eye that it's seeing something. It's seeing a continuous image, even though, as we've already seen, this image is getting drawn at some rate where it's reading individual pixels and updating each of those individual pixels over time and refreshing those, and it's changing those pixels based on the frame buffer in the background and how quickly we're updating that. And so what we're really doing is tricking the eye into thinking that it's seeing a solid frame when really it's just seeing a bunch of updates over time. So the absolute minimum for motion portrayal, you can get away with 8 frames, but it's probably uncomfortable. But anything below probably 10 to 12, and again, it probably depends on the person a little bit as well. It's the absolute minimum. If you're hitting below that, then what you think you're seeing are just individual images, and it can be very headachy. Even at below 16 frames per second, it's a visible stutter, and you'll usually get a headache. So 24 frames per second is what most movies are shot at. They feel smooth, and you certainly get the perceived motion, but it's not as smooth as it could be, right? And if we go all the way up to the top, then 60 frames per second is kind of our sweet spot. So this article, it's claimed that so that website claimed that science hasn't proven that we know what the theoretical limit is. I don't know that anyone can actually justify it other than people who make broad claims on the internet. But probably there are individuals who can see somewhat above 60 frames per second, but it's probably not going to be much above. It's probably going to be on the order of 70, maybe 80 frames per second, but certainly not 100 or 120. Well, okay, so if I just made the argument that we don't need higher than 60 frames per second to be able to render, why are all of our benchmarks showing us huge numbers of render rates, right? So why is like the GTX 1080 when it first came out showing 161 frames per second on Doom? Well, there's a couple reasons for that. One is that bigger numbers sell more, and so it's certainly always feels nicer to have the highest number you can possibly get. But what that means really, and this is the part we'll get to, is if you again think about our full engine update loop, the less time you're spending on rendering, because you're rendering at such a high frame rate that it's a tiny amount of time that's spent rendering, right? So it's 1 over 161 in this case seconds that's spent to render a single frame. That means that you have a lot more time to do all the other parts, right? You can actually do some more complicated physics, or you could do stronger AI. You can spend a little bit more time on your update on that. And so really that's the important piece, not so much that you might actually render the full game at 161. In fact, that's a reason that we'd want to stick at the full game at 60 frames per second, take advantage of this very tiny window of rendering, and then use the remainder of our time to do some far more interesting things, increase the player's experience beyond just the visual in terms of the gameplay that they're interacting with. So what about movies? I said that movies only use 24 frames per second, and that continues to be true. In fact, it even feels weird if you see something like The Hobbit at 120 or 240 frames, whatever it was rendered at or captured at, because it starts to feel low budget. You actually see the makeup and you see the bad effects of it feels more like you're going to a play than seeing a film. But what's happening in terms of the actual motion is that a single image, especially on a film, a single image is being exposed onto that film, and it's exposed for a certain window of time, so 1/24 of a second, and things that are moving fast enough blur. And so you actually capture that blurring on that single frame. And this is what's known as motion blur, right? So films do this for free. Films actually capture motion blur for free. So rather than a crisp image, you get essentially a blurry image. And so most films that you see, especially rendered at 24 frames, and they're shot that way, and they end up showing on the screen, on the projection that way, look blurry. And what you lose is a lot of that detail that might make you think you're seeing a stage play. You're missing the makeup, you're missing the small errors in, say, the stage set design or whatever. And so it feels a certain way, and we've gotten used to that. And so that's why that film feels better than, say, a higher frame rate for movies in many cases. So the motion blur is free for movies. Turns out it's actually fairly expensive to try to compute that for video games. There's a couple tricks to do that with shaders to try to add in that motion blur, especially full screen motion blur when you're moving the camera. Um, it can be pretty nice when that works, but certainly we can't, unfortunately, get away with 24 frames per second rendering in video games, except maybe for cutscenes. Okay, so assuming we're sticking with 60 frames per second for our games, because we kind of need to, motion blur or not, that doesn't leave us a lot of time, right? So, let's assume that we need 1 millisecond for player input. We still have another 15 milliseconds, which is great. And what you can think of is with that last 15 milliseconds after we do the player input, we can decide, do we spend 10 milliseconds rendering and only 5 milliseconds doing the update, or do we spend 5 milliseconds rendering and 10 milliseconds doing the update? And this goes back to why we might want a fancier graphics card, or why the fancy graphics card exists to help us do that stuff. The problem you run into is that if you want to make a game that works for everybody and feels a lot similar, you can't really make the gameplay at the 10 milliseconds rate, right? You kind of need to make the gameplay at this 5 milliseconds rate, and anybody that has a better card simply gets a better frame rate overall, gets a better update time. And the reason for that is that the logic update piece, the more time you spend in here, the AI might be more advanced, right? Or the physics might feel a lot nicer or more stable. And so if you spend too much extra time doing that on the fancier cards, then you suffer actual gameplay performance. You suffer a gameplay result, you suffer player feel if the player doesn't have a good enough system. And so from a commercial aspect, you actually sell the game worse unless you have a bare minimum. And so that is, of course, why games have a bare minimum of performance requirements. They say that, my game won't run on anything less than this kind of machine, because you want to hit a certain target. And assuming you've actually carefully crafted that target and made sure that you've optimized down to exactly all the things that you can update in that 5 millisecond window, then that's kind of your minimum, right? Now maybe if you're really lucky, you can do some simpler rendering on your minimum hardware and still give yourself a lot more time, because that's what's important to your game. But those are the kinds of decisions that you have to make then. So it doesn't leave you a lot of time. So what can we actually do in 10 milliseconds, let's say? We'll take the bigger one for our renderer. So this is what the rendering pipeline looks like, and we have to do all of these things in 10 milliseconds in order to get our frame on the screen. So we see our, come back to our rasterization and scan conversion over here, and this is the part where we actually get down to turning our screen into the pixels and the frame buffer that end up getting drawn out. So we've kind of gone over that, so we won't go over that again in much detail here. Instead, we'll focus entirely, or almost entirely, on this geometry pipeline and the fact that we have to go through each of these steps to get through and figure out what it is that we're going to end up rendering to the screen. And we'll start with the model view transformation. So just to give an overview, I guess, first, the idea here is that what we want to do is figure out, based on where our eye is in the real world and where our 3D objects are, we need to figure out if we can see them, and then we need to project them onto this screen. And then after we've projected them onto the screen in this way, then we can render it as we'd expect, right, under the frame buffer. And so we actually get to see it. So the job is, multiple steps here, but really it's kind of at a high level. Just lets us figure out where the geometry is, how it's positioned relative to the screen, and then we can see and project it. So let's take a look at how that works. So here's, this is actually in Unity, but it works kind of the same way. So we have several transformations, or several axes. So in this case, this box is oriented in this way. So we see its z-axis is here, its green and red axes are over here. We'll refer to them as just by their color, since they're a little different than in Unreal. And this box is actually positioned in the world. So our world space is positioned here, right? So in this case, we've got green up, red forward, and blue to the left. And so our box in the world space is positioned over here in, say, 25 red, or something like that. Or maybe 4 red. We'll look at each of these boxes and call those 1, 2, 3, 4. So around 4, 3.5 on the red, a little bit on the green, maybe a little bit up, and a little bit backwards, so maybe negative in the blue. But we know, based on how we're setting our transforms, where the box is positioned. So this space here is really what we consider our model space. So as you're modeling in something like Maya or Blender, and you're defining where all your vertices go, you are centering the object somewhere as you're building it, and that's really what we're talking about here. So each of these vertices for the default cube are positioned so that the origin, or the model space origin, is set in the center of the cube. Now often with characters and things like that, the model, or the origin, is set between the feet. So you render a character in like a T pose or an A pose, and you put the origin position at their feet and then render everything else relative to that. And the reason for that is really that you can then position the object in space, in this kind of space, somewhere on the ground. So the green value would be 0, but the blue and red value would move around, and you would know that the feet are sitting on the ground perfectly given that information, right? So that's kind of where you use model space, especially when you're a modeler trying to determine where these go. But what we're talking about here is really where the vertices positioned relative to the object, and the reason that that's useful is then we can just move the whole object around and all the vertices kind of go with it, right? It's almost like a parent-child relationship with vertices, that the child will follow the parent around as it goes, just based on this offset. So what we would need to do in the first place is just figure out how to get all of these vertices transformed into the world space. And the reason we do that then is that now we know kind of globally where each individual vertex is. And given that, we have this other transform. So we also know in the world space where our camera is, right? So in this case, this camera is at -3 on the blue and around 0 on the red, and something like 1 or 2 up in the green, right? And it's also looking in this direction. Okay, so it's looking along its blue axis here, and its red axis is the upwards angle, and the green axis shows us, the right hand, just to sort of orient us, but really we only care about the red and the blue. And what we want to know is where each individual vertex is in the space of the camera, because then we can figure out whether or not the object is visible to the camera. So if we have it in the camera's space, and we already kind of saw this over here, this is the same view, right? This is our camera here, or our eye, and our screen is somewhere over here. So our eye position is here, and our screen position is here. And then based on that, once we get all of these objects transformed in, we can look at them. Now the reason that we don't just do the position of the object is because really the position of the object could be sort of arbitrary. We already said it could be at its feet, it could be at its head for some reason, it could be at its waist, or it could be in the center of the box or the bottom of the box. What we really care about are where all the vertices are and whether or not we can see them. And so that's why we transform it from the model space all the way over to the camera space. So we kind of need to do true transforms, because we really don't know what the relationship is between the camera and the box unless we go through world space. We know both of them in world space, we know each of them individually, and we need to move through 3 spaces, right? We move from here into world space, and then from world space back into camera space. So what that looks like is what's known as a model view matrix. And we'll kind of skim over the math. I'm going to show you the math here so that you're aware of it. We're not going to worry too much about the details of that. That would kind of be out of scope for this class, but it's important to understand what's happening and why it's sort of, really what's happening on the graphics card, and why it's actually pretty straightforward to do. So in the first place, we have a matrix where we're really representing the red, the green, and the blue lines as their XYZ vector position, where we can think both of vectors as being a direction or a position in space, and it's always really, when it's a direction, relative to an origin. And so here, what we're looking at is, here's our origin, and we can think of the green as a vector from that origin, and the blue is a vector from that origin, and these are directions in the world space, right? So if we come all the way back over here, what we're talking about when we say the x, y, and z value of this vector, it's really this direction if we were to look in this direction from the world origin. Now we positioned it over here, and that's because we store our position for our cube itself, but the rotation we keep track of is really kind of a reference, a vector, a direction that is based on the world origin, or just, can be sort of positioned anywhere because it's position independent. So we still have an XYZ value for each of these vectors to represent sort of where they are facing in the world view. So given that we know that, it turns out that the transform that we use is essentially just those vectors either in the columns or the rows. And the difference between the two is whether it's a normal transform or an inverse transform, right? So the normal transform, if we multiply any given vector or any vertex location within this matrix by within this space by this matrix, what we actually end up with is a transformation from the local coordinate system into the world coordinate system. Now we do have to add the translation, so that's just really the orientation of the box. And so if all we did was rotate all of our transform all of our vertices by that matrix without accounting for the offset of the box itself, where it's positioned in space, we would get the cube sort of positioned at the zero space over here. Okay, so you can picture that the rotation really just positions the cube over here because it's still positioned at its center, and we're kind of ignoring how that center's been offset. But all we have to do after that is add the translation back in. Okay, so we rotate and then we add the translation, and that positions all of these vertices in world space. Now, given that we've got all of them in world space, we only have to do one more transformation. We have to understand how to go sort of the inverse to get them into the camera space. So it's almost like taking, they're defined in this space, we're going to just sort of transform them into this space. Pretend like you're now over here and defined by all of these vectors, right, locally. And so that's really what we're doing. So now we've got them in world space. We understand how our camera is set up in world space with both its red, its green, and its blue vector here. And we use the row-oriented version of our vectors simply because we're transforming from an inverse. We're going from the world to local space. And so the first thing we need to do is actually subtract the translation, right? So we subtract our rotation relative to the camera simply to sort of undo this, right? So the first thing we did was rotate and then add in the translation. Now we're going to subtract our translation, and this is the camera's translation. So this is the position of the camera in space over here. We subtract that from our vectors, which then tells us that we're looking sort of this much further away, and then we rotate everybody based on that. So again, we subtract our translation, we get our positions relative to where the camera is sitting, and then finally we do our inverse transform, which now positions every single vertex in the camera space, right? So all the values are sort of relative to these vectors here that we're looking at, and that now tells us essentially everything we need to know to understand this initial question over here. Are these vertices viewable by the camera, or are they not? Okay, because they're now all positioned relative to these vectors over here. Now, one other trick that we can do here is we can actually combine this whole process into a single matrix operation, a 4x4 matrix operation, but we'll kind of ignore the details on that. And that's where you get something like the model viewed matrix. Okay. So we're going to skip over the vertex shading and illumination. That's a little bit of an older process. That's really when we try to color by vertex or shade by vertex, or even do lighting per vertex. And we don't really do that much anymore, especially in the modern game engines. We can afford to always shade and color by at the pixel level. So given that we've got these all in our space, right? So again, coming back to our picture over here, so we have our objects in the space. We now need to project them down onto the screen so that we understand, things that are further back need to be smaller, and things that are closer up stay large or stay whatever size they are. What's behind what, to make sure that we're not rendering in the wrong order and all that kind of fun stuff. So a little bit like the painter's algorithm and all those things. So that's what we do with the projection space. Really, the projection just tells us what is on the screen, and then we have to figure out how we're actually going to map it, right? So perspective correction is the real process that happens where things that are further away end up appearing smaller, right? And that is in part due to the angle that we're looking at here. And so we pick a field of view angle, and again, if you look at the definition that I had over here in the same way, we can either change the distance from our screen here and assume our screen is a fixed size, or we can say we know that there's this distance here and we change our field of view. Okay? And this is actually one of the reasons that you end up getting a little sick when you play video games, and the field of view doesn't match what your eye is expecting. So if, say, you are sitting at a computer screen, this is probably only a foot or maybe a foot and a half distance here, right? And so your field of view, in order to match the given screen size, right? So you can't actually change the screen size on your computer screen. You just get what you have. But given your screen size and how far you're sitting away, that defines a field of view angle here. And so if that field of view angle does not necessarily match up with what you are expecting, because you're sort of making a larger field of view or a smaller field of view than what you should be, given where you're sitting and how close you are to the screen and how big your screen is, then you might get sick because it's sort of a mismatch in your eyes thinking something really bad is happening. So for instance, when you're pretty close to your screen, you might actually be able to get away with, say, 80, 90 degrees field of view, right? And so a lot of FPS games are written with 80 to 90 field of view because that's kind of the standard, especially for a screen, computer screen, and the right ratio and all that now. And usually we use the width as the ratio, and then we just kind of figure out what the height should be, height, field of view, and the height size based on everything else that's sort of set there. But we take something like 80 degrees field of view and call that good, right? Because we're about 1.5 feet. But that doesn't match up necessarily when you're playing on a TV screen with an Xbox controller or PlayStation, and you're probably more like 5 or 6 feet back, right? Especially if you're sitting a nice comfortable distance away from your TV and not really up close to your TV. Your TV's larger, probably, than your computer monitor, but those two factors then mean that probably the field of view when you're playing on your TV should actually be a little bit smaller, right? It should be maybe on the order of 60 or 50. Sometimes they'll keep those distances there, right? So even though you're on the computer screen, it might be rendered as though it's 60 to 50, 60 field of view, and it doesn't feel right. It feels a little bit too narrow and a little washed out, or maybe the field of view is a little too wide, and so it 100 or 110 or something like that, and then your eye feels a little bit wonky, especially at the edges. It looks like it's swimming a little bit. Now there are potentially other factors that are involved, but that's at least one where you could really potentially calculate exactly what field of view you should see to match up with how you're sitting in your computer screen. You could take a ruler out and kind of measure that and understand the angles. So if you picture that we draw a line from our eyeball out to each corner of our screen, and then out all the way out, we sort of see that the far plane, the distance that we're seeing, you can imagine a giant computer screen sort of 200 feet or 1,000 feet away from you, that's sort of a mirror of your own computer screen, right? So each of these lines, you just draw them out for 1,000 feet, and you get a much larger screen. Okay, so we take that, and now we know that screen, if you just simply were to render that computer screen onto yours, or whatever image was out there, this giant screen that's 1,000 feet out and so much larger, say 1,000 feet by 1,000 feet, 1,000 feet wide and maybe 800 feet tall or something like that, right? Because of these lines, that would fit perfectly on your screen, right? So when you're looking at something 1,000 feet out, it should be around, I'm going to use arbitrary ratios. It'll be a very giant screen, right? So this very large screen, 1,000 foot wide, 800 feet tall, fits exactly to within your screen here. So any object in this sort of imaginary space we're talking about that's around 800 feet tall and about that far away from you should fit on your screen, right? Now it should be, things that are closer up will cover up part of that object, and you still have sort of that depth issue that you need to deal with, the painter's algorithm as we talked about. But that's kind of the scale at which we start to render these things. I guess there's some potentially complicated reasons for why the scale increases. I would point you to some physics classes to look at that, but a lot of it has to do with the fact that you could imagine an angle of light coming into your eye, and so you could imagine all of the possible ways your pupil could see light all coming in at an angle, and so all those lights come in and then get projected onto the back of your eye in much the same way that we're projecting them here. And so because there's an angle to the projection that goes into your eye, we're doing an angle to the projection that goes to your screen, and therefore we end up with things sort of shrinking because of that kind of projection that's happening. So the further away things sort of get squished because there's an angle involved, and so on. Now I'll kind of leave it at that and let you also take a look at this far plane over here. This is if we were to render directly into the screen where we have all straight lines, then we don't have any of that perspective correction, and what we get really is no sense of the depth, right? So things that are far away end up being the same size when they're close up and we project directly in. But what you can also imagine here is another way to look at this. So we talked about the 800 foot tall character standing back here and fitting on our screen. You can also imagine stretching, right? So you either squish this rectangle down until it fits into this space, or you stretch this rectangle out until it fits that space. and you sort of stretch things based on how these lines are bending, right? So we have to bend these lines out or these lines inward, and so we bend the shapes that are nearby in the same exact way, right? And so by bending those shapes, we end up then, once we've bent everybody, then we project them directly on the screen this way. But of course the red ball is a little smaller because it got bent a little less, or it got bent a little more because it's way out here, or maybe the yellow ball gets bent a lot larger, it gets scaled up because all these lines are closer up and we're stretching out this screen to make it fit. But that's a similar maybe idea to what's happening. So the projection matrix is also a matrix, right? So after we've done our model and view correction, the projection matrix is always a 4x4 matrix, and in part that's because we essentially what you do is you take a vector that is 3 long and you add an extra 1 on the end of it. Okay, so by adding an extra 1, now it's 4-dimensional vector, and you can do this full multiplication. And what happens is after you've done this full multiplication, that 1 becomes something not 1 anymore, right? It becomes it becomes whatever it becomes, right? It's probably something on the order of ZF times ZN, ZF minus ZN here, and that what you do is then you divide, you divide by the size of whatever that number is. We usually call it W. So we've got X, Y, Z, and W, and if W was 1 and now it's say 3, you need to divide everything by 3 in order that W is then 1 again. And so by doing that, you sort of get to include an extra little scaling factor into all of your code to make sure that it goes from, whatever it is to back to 1, right? So the W always has to stay 1. And so that's kind of the trick of having these 4x4 matrices, and that's the trick that's taken advantage of by the projection matrix here to add an extra scaling. And so the scaling that's happening here is essentially a linear projection. It's pretty much this exactly here, and what we're doing is taking like our screen width, or whatever screen width or screen height we're dealing with when we're actually in this space, right? So oftentimes we might say that our screen, so if we project everything into the camera space, we might actually want to know that our screen is say 2 meters wide in camera space, right, and maybe 1 meter tall. So if we were really come back over here, we would actually be looking at a screen which is, say, 1 of these boxes tall and 2 of them wide in order to understand the real screen width. And then we take the distance of the Z near plane, which is often very close. It's usually like 0.01 or 0.001 or even 0.0001. And that's kind of how far we say that the camera is from the screen. Now we could actually set this ZN value to something closer like our actual distance, right? So we might set it to 0.3 meters, which is like 1 foot, or 0.4 meters or something to get closer to maybe 1.5 feet or something. And then the Z far is really the far projection over here. It's how far this goes and sort of the distance that we're going to see, the ratio between the two and so on. That helps us understand, and really mainly what's happening now is we're dividing by the width, we're dividing by the height, we're dividing our x by the width and our y by the height, and our z gets normalized. And so what we end up with is sort of everything after the projection. It's not projected to the screen, it's now sitting in a space where actually I think it's -1 is here, +1 is here, so we're -1 to +1, -1 to +1, and then 0 is the near plane and 1 is the far plane. And so given that, we know that anything with a z value of negative anything is too close to C. It's actually behind us in some sense, or inside our screen. And then anything with a value greater than 1 is outside of our screen. So we've normalized everything, so all we're dealing with is zeros and ones essentially. So that's really what we come into here after the projection. And then given all that, we sort of, again, we sort of done all the scaling and moving everything, again, sort of this picture where we're scaling, bending things based on how close they are or far away, so that what we have now is, you can almost imagine this box is a 1 by 1 by 1 box, or a 2 by 2 by 1 box, or whatever, for -1 to +1 and so on. But everything's very orderly, right? And now what we have to do is a very simple kind of check on everything before we render it to the screen. Okay, so let's get into culling and screen mapping, and really we're going to be talking about doing a little bit of rasterization here as well, or at least rastering from the triangle into the frame buffer. So let's take a look at that. So let's say we have our triangle now in our projection space, and we could simply render it to the screen given 3 vertices. Okay, so we've transformed all our vertices. We've gone through from where they are in the model space into the camera's space. We've projected those vertices down into a uniform space, so they're from -1 to +1, or even from 0 to 1 in all 3 forms. And then understanding that, we now know that we can position this point in space and say, well, if it's 0.5, right? So let's pretend our screen is only this size, right? And for whatever reason, we've got a 10 by 10, I think that's 10 or 11, 10 by 10 pixel view. Okay, so our triangle now has been defined, and we projected it, so we're in clip space. And what we're saying is our point here is around 0.5 and say 0.1 down, right? So it's not 0, it's 0.1. And so we measure that and figure out that is roughly half the pixel's width, right? Or half the pixels over. We take actually 0.5 times the number of pixels along our width here, and that gives us exactly the pixel position for that triangle. Now it might be 0.52, and so it's a little bit like you could almost think of it as a partial pixel value, and there's some things we can play around with that. But for now, let's just worry about the fact that we know that it's this pixel, right? And so the same with these other 3 vertices. Okay, so we can actually go through and figure out which pixel each of those vertices lands on, and then all we really need to do, in some sense, is say, are these pixels that we're trying to render for this triangle inside or outside our triangle? And we might do like we see here. This is actually an anti-aliasing trick. So if we're kind of partially covered by our triangle, we might partially draw that pixel. And so that's actually what happens with anti-aliasing. We only draw full dark or full color. So this one's a black triangle. We would only draw the full black color for those pixels which are fully covered by the triangle. And the ratio at which they're uncovered by the triangle is the ratio to which we draw less than black. And if you were to stand far enough away, you would see a triangle that looks pretty much like it fits this shape, right? So we're kind of playing that same trick again, where from far enough away, your eye blends things together and just sort of makes the right image appear. Now the edge ends up being a little bit fuzzier, but it ends up being sort of cleaner in the end. And so anti-aliasing is a very nice trick. The idea of aliasing really is the fact that because we are not precise enough, the aliasing is always because you are undersampling. Is that our pixels are too large, right? So we really need a very small amount of pixel, or a very tiny pixel, to really represent this triangle correctly. And so every pixel is always too large for the right level of triangle, right? No matter how careful you are, there's always some error you're going to accumulate. Okay, so the aliasing says we're going to sort of alias a higher dimension than necessary, or we get a higher dimension or higher frequency than we expected, simply because we're unable to capture the right frequency. And so the higher frequency means that we get jaggy edges. So jaggy edges are like a high frequency edge, whereas a smooth edge is a low frequency edge. And so we're aliasing in higher frequencies. And you can really see that, if you were to go and do Fourier analysis on that, you would actually see higher frequency data show up in your Fourier analysis. But if you're not familiar with Fourier analysis, then it doesn't matter. And just understand that the term aliasing simply means that we're getting extra jagginess that shouldn't be there. We're using too few pixels to represent what we're trying to actually show. And so if we were to add more pixels, we would actually get less aliasing. But of course, again, there's only so much resolution you can get, and the real world is almost infinitely deep in its resolution. Okay, so we'll come back to actually figuring out which pixels are inside and outside when we're rendering a triangle. But let's understand how this triangle fits. So there's a couple questions here. One is, why a triangle? Why not a quad? So often, in this character that we see here, we actually see essentially that it's been modeled as a series of quads that have been split into triangles. But you see a whole bunch of these patches are essentially, sort of square shapes, not really square shapes, but quads or rectangles or what have you, trapezoids. But you can imagine that the modeler who took this put down this 4 vertex patch to represent this part of the body. There's a lot of reflection going on and so on. And so it makes a lot of sense. It actually feels very comfortable to model with quads, to model with rectangles as patches when you're doing that modeling. So why wouldn't we just take those quads back in? Well, there's sort of two problems ish with them, or kind of the same problem in different ways. So one problem with the quads is that it can bend, right? So when the quad bends, it we could have our vertices. We've talked about all of the weird transformations that we're doing with our vertices, and so if we got it wrong, then we are not necessarily wrong. If we bent our vertices sort of in inconsistent ways because of whatever might be happening that causes those to bend, then we have to decide, well, okay, we have to break this quad. It's no longer going to be a flat plane of any kind or flat shape. We could still move these triangles around, but it doesn't really represent a plane anymore. And so we kind of have to bend it in some way, but there's actually two bends that make sense. One is the bend here, and the other is the bend here. And so both of those bends are sort of accurate, and we don't know which is the right one. If we were to start with a quad and then bend it, we'd have to just sort of pick which is the best. And so often the modeling tools help us out. So the modeling tools give us something like this, where they say, well, here's a bunch of quads, but we're going to go ahead and pre-break them for you, so that as you start to bend these things, for whatever reason you're bending them, you bend them around the triangles. So then the other question is, why a triangle, right? Why not some other shape? And it turns out that a triangle is very stable, right? No matter what you do to this triangle, no matter what transform I put on these vertices, I always get a triangle back. Now I could get a degenerate triangle. I could get a line, because this if I were to squish this direction, I would just have this line here. But in some sense, we could still treat it. We could treat those three vertices as a triangle, and just some of our sort of algorithms would suddenly sort of skip this extra step, right? So as we're trying to figure out if we're inside or not, we'd really only figure out the pixels along the line are the ones that are inside or out, or are the only ones that are inside at least partially. Every other pixel is outside, but we could still kind of do the inside-outside test with a very narrow. You can almost think of it as a almost infinitely small triangle, right, or an infinitely narrow triangle. But it's still more or less a triangle, right? And it's the same thing if you were to make all these three all within this single dot. Now they only exist in a single pixel, but you could think of it as a very small triangle in terms of the algorithm, even though it's all in the same position. So the degenerate cases can still be thought of as triangles in some sense. And then there's another sort of advantage that we can get to, where even if we have quads and all that, we actually turn our whole model. So we take our whole model like this, and we turn it into what's known as a vertex buffer and an index buffer. And this makes it fairly easy to, now technically we could probably do this with a quad buffer as well. You sort of think of the quads as being the same shape. But again, we've already gone through why we might break up the quads, so we won't worry about that. But this ends up being a very easy representation to help us with even more of the transformations that can happen, right? So if we picture that we have all of our vertices defined in this array, this is all the vertices of our model, right? So this is all the vertices that make up this cool character that we're trying to render, say, in this case. So we go through and we say, okay, vertex 1 is here. I'm calling them A, B, C, D, and E, and F. And these are vertexes, right? So these are three values that are stored in this. So there's an XYZ in here, and there's an XYZ in here, and so on, that represent all the vertices. But we only represent each vertex once. And if it's shared, if it's, say, a vertex that is right here, or let's look at this model, let's say this vertex right here, it's shared by 1, 2, 3, 4, 5, 6 triangles, right? This vertex right here is shared by 6 triangles. We will only put it in the vertex buffer once. When we draw the index buffer, we will reuse that number over and over. So as we draw our index buffer, as we're drawing to say, well, A, B, and C represents triangle 1, then I am going to represent that triangle only with A, B, and C. But then B, C, and D also represent a triangle. So I've now reused B and C to represent triangle 2. To represent triangle 3, I'm going to reuse C and D again. So now I've used C 3 different times, right? So in my index buffer, I do write down value C, or the index C, 3 different times in my index buffer for it to be used for each of these 3 triangles. So this is another reason. This is maybe not a justification for triangles, but this is a reason for the index buffer. Again, because we are doing all these kinds of transformations, because we could have floating point errors, because we could have slight differences between them, if we were to recompute for each of these triangles the vertex here, we might actually get slightly different answers. And when we get those slightly different answers, When it comes to actually rasterizing the values, we might actually pick a different on or off setting for a triangle based on, or for a pixel based on where that's sitting. And so what ends up happening is that you get gaps. So if you don't do something like this, then you end up with small little flickers of light as you're moving through space, or as your camera's offsetting, or as your character's animating. You will actually see little, like, flickers that say C was differently calculated for each of these each time, and caused all kinds of problems. So we don't do that. So really, we keep these index buffers in place. We don't repeat our indices, and what that means is that all of these triangles look exactly the same projected vertex value for C by just indexing into this array. So we go through this array once. It's actually efficient as well because we don't multiply it for each of our triangles. We go through this array once. We calculate all of our offsets and transforms to all of our vertices. Again, we're still kind of doing the whole vertex transformation. And then we just look up in our index buffer. Our index buffer doesn't have to change at all. We define it once for our entire model based on where we put all the triangles. And that never changes because it's really only the triangles that are underneath that are changing and modifying and changing shapes. You can imagine this B's moving, this A's moving all over the place with skeletal animation and transforms and projections and all of that. All those values are moving in all kinds of crazy ways. So the vertex buffer is going through absolutely insane transformations, but the index buffer doesn't really change. It just goes and, again, looks up exactly the same A, B, C vertices to figure out triangle 1. But of course, because the A, B, and C are changing so dramatically, triangle 1 is, of course, very different every time we draw it. So hopefully you can convince yourself that a triangle is always always a triangle on the screen, no matter what you do to project it, or rotate it, or squish it, or reshape it. It'll always be some sort of triangle. Or the only weird thing you can do is make it a degenerate triangle, like a line or a point, right? Except if you're clipping. So the clipping is kind of the one case where we actually break all that, right? So if we look at this clipping here, this is my triangle, and I ended up doing some kind of weird transformation to it so that it's actually projected completely outside the screen. So this is one case where we do actually need to be careful about how we figure out the inside-outside of whether or not our camera can see this triangle. If I'm looking at just P1, P2, and P3, they are all outside my clip rectangle. So you can think of the clip rectangle as after we've projected into the screen, then these coordinates are 0 to 1 or negative 1 to 1 or whatever, as we said. And P2, P0, and P1 are all completely outside the screen. So we do have to be a little bit careful about how we figure out whether or not something is visible or not, especially if it's so large that it sort of takes up our entire view, as this particular triangle does. Okay, so given that, once we know that this triangle takes up the space, we have to figure out how to clip it. And so what happens is we end up having to clip the triangle. The clip algorithm actually does something like this. It'll walk from intersection points of the triangle to the screen and essentially walk a new polygon. So it actually starts at, say, P0 here. It happens to go from P0 to P2 and figure out where the intersection point is, arbitrarily, somewhat. Could have found this one instead. And it'll start walking lines to figure out where all the intersection points are and sort of rotate through and determine that we've got this shape, right? So this is the shape that we have to render, and it's a new polygon. It's now got 7 vertices, and we're kind of, in trouble because now we no longer have triangles again, and yet all of our algorithms are kind of expecting to be working with triangles, right? All of our rasterization rendering stuff wants to work with triangles. Well, it turns out that we don't really have to break that much, right? So we go through and we figure out, where the edges are and do this. And we do this for every triangle, so we actually clip every triangle unless it fits entirely within the screen, then we don't have to clip it. But we're probably going to have to shave off some part, and we're going to get a polygon out of that, right? So if you just pictured a triangle that fit, say, here, it actually ended at this point where I'm drawing my mouse, we'd still have to chop off this corner, and so we'd end up with a shape that was not a triangle anymore, no matter what, whenever we clip it. So you can already see the answer here with these blue lines. This is one of the ways that we can simplify a polygon back into a triangle. It's called the fan, a triangle fan. It's a little bit like an index buffer, but in this case what we're saying is we start with P0 and we go to P1 and P2 and we say draw that triangle. We've got 3 points, let's go ahead and draw a triangle. Okay, so starting with P0 again, continue on from P2 to P3 and draw that triangle, right? And then now we start back at P0 again, we go to P3 to P4, and now we draw that triangle, and so on. And we simply just walk the same edge as we're clipping. We say, okay, I'm walking this edge and say, all right, I've got 3 points, let's go ahead and draw a triangle, move on. Okay, I've got these 3 points, I've got a triangle, move on, and so on. And then once we're done clipping, once we get back to our original point by sort of walking around the outside triangle and figure out where all the intersection points are, and we draw our inside triangles, we're back to triangles. We've got more than we intended, but that's okay. We can draw them pretty quickly, but our algorithm doesn't have to change. Right? And really the amount of time that we spend is more about how many pixels that we're drawing in this space, and so we didn't change the number of pixels that we have to draw at all. Okay, so before we get into rasterization in depth, let's spend a minute and talk about linear interpolation. So the idea behind linear interpolation is that I can take a point, a p0 here. We can think of L as our length, the length of the full thing, and I vary this t parameter, which is often time, say, or just a parameter that moves us through this space, called t by convention, I think because of time usually. So if we start at t0, then we start at our main point, right? And if we let t go all the way to 1, then it's going to move us along the line here. And we could look at t at point 1, and we'd be here, and point 2 here, and point 3, and point 4, and point 5. I sort of scaled that wrong as I was stepping through it, but you can imagine. So 1, point 1, point 2. We can even look at t.001, which would put us right here, or t.459, which would put us like right here. So we can kind of vary t however we want, and we can pick any point along this line, right, up to where t equals 1. So we always kind of stop with t equals 1 and say that's the end point, right? So you can also imagine that this is p final, and so we could set this up either as L or as p final minus p0, which is still equal to the length of the line that we're actually doing. And the length doesn't have to correspond to anything. It could be 10, it could be 25, it could be 100, and so on. But this moves us through space, right? And this really works not just with simple values that are moving along a straight line, but actually any vertex, so any vector. So if p0 could be a 3 vector, and then p final could also be another 3 vector, and then the length is also a 3 vector that sort of represents the direction and length between these two. And so when we're multiplying t by the vector, then it's really just adding it to p. We're really just picking a point in 3D space, wherever these 2 points are. Any point, any position in between these 2 points in 3D space, assuming they're a vector, we're picking out that position. Okay, so we're going to look at linear interpolation along our triangles. So I've offset these just for the view, right, the visualization, but imagine that this black dot lines up with the red, and this black dot lines up with the red. And so we're going to walk along this line here, along the dotted line. And what we want to do is essentially just move. We're going to set our t values such that we move from this pixel to this, well, to this point, to this point, to this point, to this point. And what we're doing is moving along this line by a row at a time. So we're saying let's start at the top row and move down exactly 1 row, right? Move down exactly 1 row and exactly 1 row. So we're going to step our t to move us down to the next row in the pixel, okay? And then what that's going to do is give us not just moving down 1 row at a time, it's also going to tell us how far along, how many pixels to the right we're moving. So here we haven't really moved a full pixel to the right, we've moved like a half a pixel to the right. So we really kind of consider ourselves still in this pixel. But at this point, we've now moved ourselves 1 pixel over, so now we're in this pixel, right? So we started here, and now we're here, and so on. And so we can figure out at each point which pixel we're in as we move down this line. And the way we do that is that we take essentially the number of rows that are taken up, so around 12, say, and we're on pixel whatever, 1 here, pixel, we'll say that's pixel 1, and this is pixel 2, so we're going to move down to around pixel 13, pixel 14, somewhere down here, right? And so it's 12 pixels, so we take our whole line and we say t is, our t update goes, we want to go to 1, right? So t goes from 0 to 1, remember here, and what we're going to do is update t by 1 over 12, so 1/12. So the first pixel starts at 0, and we move 1/12 over, which I'm not sure exactly what that is, but it's like 0.08 something, or 0.09, I'm not sure, but we don't care, it's 1/12. So we move t by 1/12 over, we use our calculator to figure out exactly what that is, and that's our first step. And then we move 1/12 over again, so now we're kind of 2/12 over, or 1/6. Now we move 3/12 over, so 1/4, and so on. And so we're moving by that speed, by 1/12 of the whole length of this thing, but what that does is moves us exactly 1 row of pixels down. Okay, because we got 12 total pixels. Oops. and we move one pixel down to move along this line in rows. So then, as I sort of skipped ahead, we do that on both sides. We go not just from P0 to P final over here, but we actually go from P0 to P1, and we'll continue to call this P final, but we could also think of this as P2, right? And so what we do is we do the same thing over here. So we say, okay, well this one is 12 pixels that we have to jump through, so T over 1/12 over here, but over here it's 1, 2, 3, 4, 5, 6, 7, 8. So it's 1 over 8. But by doing 1 over 8 on this side, and again it's the linear interpolation, we take the full length from the end point to our start point, multiply by T, and we say, okay, so T is 1 over 8 here, but that puts us here. So we've got horizontal lines, we've moved along our two sides here, and now we're talking about horizontal lines. So let's use new numbers, H0 and H1, and what we're doing is linear interpolating from H0 to H1. So really we only walk through this one pixel, but we'd say, okay, how many pixels do we need to walk? We need to walk 3 pixels wide, so or 1 pixel wide, so T is 1 over 1 or 0.5, whatever, and it ends up there. In this case, maybe T is 3 pixels wide, so we start with 0.3, 0.6, and 0.9, and it moves us from values of H0, right, as our start point, and we linear interpolate, and we get each of the single pixels in here. And so by moving from the pixel that is under H0 to the pixel that's under H1, and we mark those off, and in this case we're not worried about anti-aliasing, we'll just say we're going to either mark the pixel on or off, or fully black or fully white, depending on whether we are drawing the pixel or not. Okay, so any pixel that we're drawing, we're going to write a black pixel into that frame buffer, or a black value into the frame buffer at that point once we've figured out the pixel. So again, remember that at this point we now know kind of where the pixel is with H0 because we sort of walked down P1 here, we walked down P0 to P final here, and we found H1, we found H0. So we know the pixels where H0 sit and the pixel where H1 sits, and we step through those pixels and we draw those out. And again, we do the same thing for this line here by linear interpolating to each one of the pixel values, and so on. So we've got all these lines here as we move horizontally down until finally we get down to here, right? And so once we get down to this triangle or this line, then we need to switch and say, okay, from P1 to P final, let's take those lines and do the last little step here. So the last 4 or 5 lines that we need to walk. We do T, again the same algorithm, we just sort of pretend that we started here, or we start from here and draw this last little half a triangle over here. So this is where we would need to worry about degenerate triangles if P1 was over here, or if P final was the higher one. You could think of if P final was the higher one and P1 was the lower one, you'd have to sort of do a couple branching conditions to say, all right, which one am I switching to? But essentially you just walk down and then you sort of do the first half of the triangle and the second half of the triangle, because you're always going to have that situation. The only real degenerate case then is P1 is actually on the line over here somewhere, but you do the same algorithm, and what you find is that H0 and H1 are almost exactly the same value every time you come through. Okay, so even though you're doing this interpolation with these, doing the full algorithm with the whole set, it turns out that your H0 and H1 are almost exactly the same value, so you just draw the one pixel that they're on, and you end up drawing the line, right? Now you could simplify and you could say, all right, if P1 is close enough, I'm just going to draw the line from P0 to P final, ignore P1. You could draw that branch, maybe some algorithms do, but it actually wouldn't be that much different than if you did try to do the two linear interpolations. Now what I will point out too is I said 2 linear interpolations, you're actually doing 3 linear interpolations, but this is what's known as bilinear interpolation, because we're really taking the linear interpolation across 2 lines. We're taking a single linear interpolation here, a single linear interpolation here, and then interpolating between those two, which is what gives us a bilinear interpolation. And a bilinear interpolation is generally what you do when you're trying to draw over an area rather than a single line. So this is sort of bilinear, biline, and we're drawing the area of the triangle. Okay, so now we've got the full triangle drawn. You can picture it all the way out, and again, if we've got a degenerate triangle, we could do the full algorithm. We could simplify and just draw the H0, but it doesn't really change it that much. It's still a triangle, even if it's one point. Even if P0, P1, and P final are all the same point, we sort of can still do the full algorithm. We only do one step in the entire algorithm. We see that we've got one step to say that H0 and H1 are exactly the same value, and we draw that one pixel and we're kind of done, right? But we could almost imagine iterating, even if all 3 points run the same. So the degenerate case is actually still very trivial, and yet we get a triangle out of this. Okay, so now we know how to get our triangles on the screen. How do we deal with rendering them without overlapping? Well, it turns out that we could, if we wanted to try to do the painter's algorithm, we could figure out, we now know what their z depth is, and we could say, well, let's draw the farthest triangles back and get closer. And we can do that, and that's pretty good. So if we draw the furthest triangles back, then draw the nearer ones closer, we're pretty good. Except there's sometimes that weird things can happen, right? So with triangles, we can't guarantee that this won't happen. And in fact, you see this in games all the time, where you can wind up with inadvertently putting your arm into a wall because you walked close to a wall, and so you get these kinds of clipping effects that happen. And so we need to deal with that. So there's no way to order these two triangles in such a way that we could do the proper painter's algorithm, as we talked about with 2D, and put one of them behind the other. Neither is entirely behind the other. So what we do instead is record a per pixel depth. Okay? So I mentioned that this whole linear interpolation algorithm works in 3D, and technically P0, P1, and P final are still 3 vectors. They are not just 2 vectors representing our x and y coordinate, but they also still represent our distance in the screen. If you recall all the way back over here, our distance in this sort of box here, right? So we sort of did all the conversion, did all the stretching and so on to make it look like this box. And so we have a -1 to 1, -1 to 1, and this goes from 0 to 1 with our z. So 1 is as far away as we're allowed to be, and 0 is as close as we're allowed to be. And so even though we're linear interpolating, we still know at every single point here, through our h's and so on, exactly what depth, what z value, how far into the screen each of those pixels are. And so what we can do is save that value. So every triangle that we want to render, we not only draw it out, but we save its depth value, its z value, from 0 to 1, to let us know how far into the screen it is, right? So you can look at it this way. So 0 is black, 1 is white, or as we've seen, sort of the strongest intensity is 1, and the weakest intensity or the lowest intensity is 0. And so if we were to just simply render our depth buffer, our z buffer, because we're recording z again, remember, we would get darker images for those things that are closer and lighter images for those things in the back, right? Now what you can do is imagine I've got a whole bunch of triangles I need to render, right? And so I'm going to first initialize this entire thing to all white, right? And then if I'm drawing any pixel, so all z equals 1, or all 255, if I'm looking at it that way, but I essentially store that value in here. Then as I draw any single pixel, instead of drawing that pixel, I say, okay, where I'm about to draw to, what is the current z value? Am I darker? Am I closer? Am I more black in the z value than what's currently in that buffer? And if I am, I'm going to go ahead and draw, and I'm going to replace the z value that's in there. And then if somebody else comes along and they're even darker than I am, then they get to draw, right? So in some sense, in the z value position, the blackest z value gets to be drawn into the buffer, right? The closest one. So it turns out the most optimal way to render is, rather than doing the painter's algorithm, it's better to draw the things that are closest first. Because those things, if I were to draw all the triangles from, say, this vehicle that's right here first, then as I try to draw this triangle, I will do that check in the depth buffer, and I won't even bother drawing any of these pixels over here. Now I will have gone through the whole process of rasterization, everything we've kind of talked about, for all of these pixels. I'll have to do that regardless. But once I actually get down to where I'm going to draw a single pixel and start looking at it, then I can skip a whole lot of information from that point on. It turns out that just getting to the pixel render is the first step, because now, especially with modern day graphics, the pixel shader is the most complicated part of all of the rendering. All the stuff that we talked about is the easy stuff. The pixel shader is where it gets very complicated. That's where we need to do all of our rendering and our lighting, our coloring, and our everything that we're going to see about materials and lights really happens in the pixel shader. So if we're able to very early on in this process say, well, actually I don't need to render that pixel at all, I can save a whole lot of time. And so it turns out that by rendering all the things that are closest with the lowest z value, the darkest z value, first, then it saves everything that's behind those. And so it's actually better to work in the opposite of when you're using a depth buffer, it's better to work in the opposite of the painter's algorithm. You still get the same effect. So you only really render things that are closest to you. in any distance. So everything behind this building doesn't get rendered, and everything behind this building doesn't get rendered, and so on. And so that's how we can use the depth buffer to solve this problem. So every one of these pixels essentially has its own depth, and as long as the green has a lower z value than the red, then we know we can draw it. And where the red has a lower z value than the green in this region, then we draw the red. And where either of them is simply drawing over the background, you can imagine the background again as being completely white, or initialized to completely white every time. So clear it out, turn to 255, then we draw it that way. The one problem that you run into is that if you were to store 0 to 255 for the z value, you would actually have quite a few problems, because you actually have triangles that get very close to each other, and 0 to 255 is not a whole lot of values to work with, right? So say they both get set to depth value of 1, right? They both kind of round to that nearest 1. Neither of them is far enough to be a 0, or neither of them is far enough apart to be a 2, so they both get set to the z value of 1. If we're looking at 0 to 255 as our z values. So because of that, we end up with what's known as z-fighting, and so if they're very close together, then depending on the math, right, we might say, oh, well, this time I started rendering the blue one first, but actually the red one was a little closer, or had the same value, but we ended up drawing the blue lines. But over here we started rendering part of the red one first, and so that one got in, and so what you end up with is this kind of effect where depending on how the math works out and how they get aligned within that z buffer, you just wind up with this. And it turns out that regardless of what we do with the z buffer, I think current z buffers are now 2 bytes big. Even though we have that many different z values possible, it's still potentially likely and conceivable that 2 different objects will be close enough that they overlap. So you kind of want to avoid this situation no matter what. You really want to make sure that your collision system and your gameplay all avoids having 2 objects sort of layered this close to each other, occupying the same depth right here, right? And so that's always something to be careful of, and really, if your gameplay is correct, this is a collision problem, right? This is a physical problem, and you don't want this kind of thing to happen. And so it's only likely to happen for objects that you're painting into the scene, or as you're doing your level construction or something like that, where you'll actually set objects this way, because then you sort of violate all the physics when you're constructing your levels, or they don't have any gameplay associated with them. So these are things to be aware of. There's really no way to solve that, because there's no depth or z depth buffer that's big enough to handle this kind of case, as long as these 2 objects are actually really occupying the same space and have exactly the same deep depth value. And lastly, we sort of have to solve a special problem with the depth buffer when we're talking about transparent rendering. It turns out that the way we do that is that transparent objects, we go back to the painter's algorithm, right? So we can't render semi-transparent objects using the depth buffer at all, because really we actually want, so this object right here, this square, this rectangle, whatever, brick that's sitting on top of these, that's the only transparent object we have. But we really need that object to be drawn in addition to the things behind it. So we can't draw the z buffer for this transparent object at all. We don't want to have it modify the z buffer at all. Instead, what we do is we sort of do 2 passes. So the first pass, we render everything that's fully opaque. Fully opaque means non-transparent at all. And then everything that's semi-transparent, of course, if it's fully transparent, then we don't render it, because you can't see something that's fully transparent, right? But if it's semi-transparent, somewhere between fully opaque, fully solid, and semi-transparent, we render those second. Or let me reiterate that. So we draw everything that's fully opaque first, okay? And we render to the z buffer. That means that if I had a semi-transparent object that was hiding behind this cylinder, I wouldn't draw it still, which is great, because we don't want that. We don't need to see that object, because the thing that's in front of it is opaque. But for this brick that we have here, for this like tabletop thing, we render that after we've rendered all these solid objects, and now we can do our blending. If you have multiple transparent objects, then you have to render them in painter's order. You'd actually render the objects that are behind this thing behind it. And of course that comes back with all the problems that we might have, where if the 2 semi-transparent objects are actually interpenetrating each other, much as we had with these 2, this one or this one, these triangle sets, there's no way to really solve that. And so when you're rendering semi-transparent objects, you have to be careful. And usually what you want is a single semi-transparent object somewhere in the scene, or multiples that are laid sort of side by side. So you're not really doing layers of semi-transparent objects. You might think of windows in a wall. All those windows are side by side, And the things behind them are solid, and the things in front of them are solid. But all of those windows are one last step that we kind of do when we draw each of our windows as we go. And they don't really layer over each other at all. And so semi-transparent objects sort of create the problem for this whole Z-buffer thing. Okay, so let's wrap up our discussion on the full rendering pipeline with texture mapping here. Again, so this is getting images onto the frame buffer and finally sort of being done with getting our 3D object onto the frame buffer and looking like a 3D object. And we will talk more about rendering and lighting, materials and lighting. You can think of texture mapping here as kind of the simplest uniform lighting and the simplest material possible. It's simply going to entirely reflect whatever character it has. Okay, so texture mapping. Really, the process is very similar to what we already looked at, except that when we are doing our linear interpolation, we need to not only find which pixel value we're in, but also what that pixel color is. Okay, so when you look at this, let's first talk about how UVs are created in the first place. So we get UVs from our modeling programs, so that's part of the art process, and we do this whole process called UV unwrapping, and we'll look at that in a second. But what that gives us is a UV value for each of the each of the vertices in our triangle, right? So if we look at these three triangles, I sort of missed the vertex over here, but you can imagine where it sits. But for each of these vertices in the triangle, we have a corresponding vertex in UV space. So you can think of the UV space as just another set of variables, right? U and V are simply to differentiate between X, Y, Z that we normally use for everything else. And it's kind of known that U and V go from 0 to 1, so we'd say 0U is here, and 1U is over here, and 0V is here, and 1V is over here. So this is like 1, 1 down here, and there's 0.5, 0.5. And so we pick different values, and again, this is the artist sort of picking these values through some arbitrary process. And so the artist is going to say, well, I want this part of the triangle to be here in the purple, and I want this part of the triangle to be here in the blue, and I want this part of the triangle to be here in the green. Really what they do is they position the triangles out, and then they paint into this texture what they want the thing to look like, right? Or maybe they actually go back to 3D, paint it over here, and it ends up changing the texture, or changing the image over here. But you can think of this really as an image file. It's usually like a PNG or a TIFF file, and it's been painted on through some paint program. And somehow there's a process by which we get these UVs here. So let's take a look at that and understand kind of what's happening. So however we ended up sculpting this cool character here through whatever process we have, so the whole sculpting process is zhuzhing the values of vertices around, pushing them in 3D space and doing that fun stuff. And you notice here that this guy has been oriented at a point between his feet. So here's his model origin. So all these vertices are offset relative to this model origin. And what we're doing is we're adding new triangles, or adding new patches, quads in this case, and we'll split these quads before we export it, and assigning vertices to those quads, and then pushing the vertices around to make this shape, right? And we add more quads, we split quads, we do whatever. But certainly once this process is done, now we have our vertices and our quads, at least, and probably triangles, all set up so we could create our vertex and index buffer. But then we want to create our UV buffer as well, our UV unwrap. And so the reason it's called kind of an unwrapping is you can almost imagine making cuts in this character and then pulling and stretching those parts out so that you fit them here, right? So you can imagine pulling the head apart and stretching it out so that it fits over here, and you cut the hands and you stretch them out so they fit over here, and all the rest of the body parts. And you do this so that you're actually fitting into a 0 to 1 space. I think you can even see, if you look really closely, that there's numbers here that go from 0 to 1 or something along those lines. And that's how we get into UV space. So there's a 1-to-1 correspondence of each of these points, or the intersectioning lines here, of a vertex. So these all represent the same vertices we see over here. And the modeling program is taking care of that for us, right? And so the artist's job is really kind of to position these and move them around to make the most sense in this space, so that they can fit as much as they can, and to probably make some of these regions larger where you want more detail, where you want more of the image pixels to be able to color, or more color detail. Some of these things can be smaller, where say like maybe his chest is a pretty uniform kind of color, so you might make that smaller because you don't need as many pixels to paint over there. And then when you're painting, you're either painting in this region, right? So you're maybe painting in the eyebrows here, or you can come back over here, so for some programs, and actually do your painting on the character over here, and it applies the paint onto the image over here. But in either way, somehow, we now have a mapping that says, okay, for each of these vertices, I've got a position on this image in UV space, so UV coordinate, right, a 0 to 1 coordinate, and I have colors in my image that represent the colors that I want that character to have at those positions. Okay, so now that we know where these UVs are coming from and where these colors are coming from, the last step for us then is, as we are interpolating, right, as we're doing the linear interpolation of our P0 to P final over here, or P0 to P1, we're also walking along this triangle at exactly the same rate, right? So if I'm looking at, I'm going to go, before we were using numbers like 1 over 12, so T is 1 over 12. So if I move 1 over 12 along the line here, I'm also going to move 1 over 12 along the line here. Now the distance is a little bit different because it's a distance in UV space. But by the end, we'll start at 0, and by the time our T hits 1, we're at the other end of the triangle, right? And that's the same for both the triangles. No matter how we're walking along them, we end up doing exactly the same kinds of walks to get us through here. But we're walking and we're capturing each of these points, and as we go along the horizontal as well, we'll have an H0 and our H1, which both represent pixel values. We'll have an H0 and an H1 that represent different horizontal lines through this space, although again it's maybe a strange horizontal line. And we're going to go and we're going to grab different color values out of here, right? And so depending on, and of course there's some fancier tricks, right? So depending on how close or far we are, we might actually grab a different resolution of texture, and this is what's known as MIP mapping. So there are ways, because there are ways that by sampling and jumping across this triangle, we actually might grab weird and incorrect parts of the color. So if you start imagining what we're doing, if we're far enough away from this triangle, we might grab this color, and we might just randomly grab that color, and we might grab that color and that color, and just grabbing this blue doesn't really represent that whole region, right? So if we were to zoom this triangle out, if we're far enough away from this triangle that we're making big jumps across the triangle by moving 1 pixel at a time, then we're going to make big jumps through here as well. And so when we're making those big jumps, instead what we're going to do is a smaller resolution image that actually captures the fact that, well, this pixel, so if we're going to turn this into 4 pixels, we get sort of a greenish here and a purplish here and a really strong purple here. We'd actually not get blue at all. And what that does is, by zooming out that way and using MIP mapping, we can avoid getting like weird errors, right? So depending on how you jump through here, you might at one time grab the blue pixel that's right there, and the other time you might grab this light purple. And so the MIP mapping actually helps us reduce errors by giving us a lower resolution image, a lower resolution version of the same image, so that as we're doing these jumps through our pixel space, through our UV space, we're grabbing pixels that make sense, right? And so the trick then is, depending on the size here, we need to grab the correct UV, a smaller resolution. So we always kind of render at the highest resolution that we care about, and then our MIP mapping process gives it a lower resolution, so that we're jumping through pixels that correspond more to the size. Okay, but that's kind of a gist of MIP mapping. That's about the extent that we'll talk about it in these classes. Okay, so that's really the whole process. It is a long process, obviously. What's kind of surprising is if we come back to what we were talking about, at the very beginning we said we need to do all of this in 10 milliseconds, and that's a lot to do. But thankfully we have graphics cards that are very fast that can do this for us, that can actually run and do all these things, all these pixels, all these triangles at this high-end performance. So let's take a look at what that means. So we could do, so a lot of the top cards, this is top-end specs relative to when this lecture was recorded at least. We can do around 16 billion triangles per second, right? So you could do 160 million triangles in 10 milliseconds. Or if you had to do the 5 millisecond version, it would be 80 million triangles, which is a lot, right? Now, depending on when you're drawing those triangles, are they on the screen, are they off the screen, are they mostly hidden by other objects, then you're still trying to go through them. Turns out that you still have to kind of pay this price for all of those triangles, but the real problem actually isn't so much the triangle counts. We can actually do quite a few triangles. The real limit is what are known as draw calls. And that's the notion that every time we want to draw a new index buffer and vertex buffer, a new character entirely, we have to go and tell the graphics card that this is our new pipe setup that we're going to do, and we have to orient the camera, and we have to orient this object, set up the model view matrices. All those things take some communication between the CPU and the GPU to say, here's the new object, right? So every single object that we have is another draw call. And every material it has, turns out, it's also draw call. And some of the setup that happens for shaders and lighting and so on, those are more draw calls. And so depending on the object, we might actually have 4 to 8 draw calls, sometimes 10, sometimes 12 or 20 draw calls per object, especially if we have more than one material and more than one light. And so it turns out that when you start to get to 10 draw calls, 20 draw calls, we can actually only render maybe 100, maybe 1,000 objects on the screen before we start running out of all our draw calls. We start using up too many. But what you can see is that, okay, given that, we do have a draw call limit, we can probably get to around 26,000 triangles per draw call. So you could almost imagine that you can have on the order of 10 to 20,000 triangles per model. Now some models you might want to make fewer, and because like your terrain might actually be a much larger model and some of your characters, but for the detailed front-end characters on modern graphics cards, you can actually get away with 10 to 20,000 triangles, and you do see that in current models anymore, that they actually can get away with this many triangles, because we really can render quite a few triangles to the screen. We're just limited by the number of characters and all the extra setup that happens. One of the things that starts to kill us nowadays is the number of pixels per second that we can deal with. So that's kind of getting through the first half of the pipeline, but the second half of the pipeline is rendering all those pixels and all the extra. We only saw the very first part of the pipeline, which is just the texture mapping to get the color on there. But there's a whole lot more that goes into it. And so for every one of those triangles, or for every one of those pixels, especially if you have a lot of overdraw, and overdraw is the case where we end up drawing the pixel for multiple triangles multiple times, right? So we draw that pixel multiple times because we didn't end up sorting our triangles quite right, and so we ended up drawing some with a higher depth value, and then others with a lower depth value later in the process. So we kind of drew them in the painter's order and ended up drawing the same pixels over and over again. And so we waste a lot of time doing that, and we run out of space that way. So even if we just look at 1920 by 1080, that's already 2 million pixels. So we can do 1,000 full screen draws in 1 millisecond. Okay, so again, if we want to make sure that we're doing everything else, we have to make sure that we also can actually render the screen. So it turns out that so this is one full screen draw, but that's only once per pixel. So if we end up drawing over the same pixels, say 4 or 5 or 20 times, because we're not being very careful, because all of our thousands of objects are sort of overlapping each other, it turns out this number shrinks very quickly, and we suddenly get to 10 full screens. But for the most part, we can pull off a lot of triangles and a lot of detail. Of course, that's why games look amazing, especially on top-end hardware. But there are some ways to limit that. So if you start actually getting very complicated objects, or you start doing a whole lot of semi-transparent layers, you end up overdrawing a whole bunch that way too. And so there are ways to kind of kill that limit. And again, this is kind of the upper limit where you don't allow a whole lot of space for everybody else to do any processing. We can shrink that, and then we can have more complicated AI and so on. So it's all about trade-offs and budgets at that point. Okay, so that pretty much all we'll talk about rendering at this point. This is kind of the full rendering pipeline, and we'll certainly come back and talk more in depth on other topics as well to do with rendering materials and lighting and so on. So stay tuned for those.